Okay, guys, I'm going to try this for like the third time. Oh, look, I had to go grocery shopping, so let me just take care of that. Um, let's uh, let's go ahead and talk about um, free response question number one. Um, we started out and right at the beginning we're asked to find what the current through R1 is, and this is a common kind of misdirection thing. Uh, there's no real good way to do that, but we could find the current through the battery. And if you notice, like this entire branch, the current would be the same because it doesn't branch off until it gets to this point, right? So the current through R1 and through the battery are the same. And so we just need to know what the load is on the battery or how much total resistance this is. First thing we need to do is combine these two resistors, R2 and R3, which are both 300 ohm resistors. Since they're in parallel, the total resistance will just be 300 divided by 2. But you can also use the rule from the formula sheet, and that would give you 150 ohms of resistance in this branch right here. They're in series with R1, and so use this rule to combine R1 with these two, which have a combined resistance of 150 ohms. You get a total resistance of 450 ohms. So that battery with 45 volts has to push through 450 ohms of resistance. That's going to give you a current of 0.1 amps. Okay, that's with the switch open, of course. Then the next thing I asked is, what is the power dissipated through R3? Now, this is on your formula sheet, the current times the voltage. And we need the current through R3 and the voltage across R3, or we can manipulate it two other ways. So you need two of the three things from Ohm's law. Right now, all we know is the resistance. But if we look at Kirchhoff's junction rule, if we have 0.1 amps, which we just figured out, going into that junction, then that's going to split up, and it's going to divide equally because these are equal resistors. And so each one will get 0.05 amps through them. But we also need the voltage across them. For that, we're going to have to use Kirchhoff's loop rule. Oh, by the way, if these weren't equal, you would just apply Ohm's law to figure out how much current was going through them after you did the loop rule we're just about to do. Okay, so the loop rule states that if I go through any closed loop path, I'll get back to zero with the voltage gains and losses. So through the battery, we gain 45 volts, and then we lose a certain amount of volts across R1. Well, according to Ohm's law again, just take the current of 0.1 amps, which we just figured out, times the resistance of 300 ohms, and we'll get a loss of 30 volts across that resistor, a voltage drop of 30 volts. And so I go up 45, I go down 30, and then I just drop 15, whether I go across R3 or if I go across R2. So they both have 15 volts across them. Okay? So substituting any of those in, you're going to get 0.75 watts for the power dissipated by the third resistor. The next thing we want to know is, hey, when we close this switch, what's the current through R1 now? Remember those limiting factors at the very beginning, at the very end. The very beginning, the capacitor acts like it's just a wire, so it acts like a short circuit. And so the battery now, the only load on the battery right at time t equals 0 is R1. And so again, we just apply Ohm's law there. But this time we use a total resistance of 300 ohms, and we get 0.15 amps going through R1 right at time t equals 0 when you close that switch. However, after a long time, this acts like an open circuit because no more charges are going to be moved from one plate to the other. And so there's no charges moving through this branch that includes that capacitor. The capacitor is full. It's up to capacity. And so it basically looks just like it did at the very beginning, and you again have 0.1 amps flowing through R1. Hey Taylor, is the time still going on my...
Yes.
Oh, awesome. Okay, so now at that steady state condition, after a long time is how they put it, how much charge is on C1? So all we have to do is look at this from our formula sheet, which was our definition of capacitance, to figure that out. The thing is, how much voltage is across it? It is not the battery voltage because it's not in parallel with the battery. It's in parallel with R3 and R2. And so it's going to have the same voltage drop, 15 volts, across it that R2 and R3 had. And so when you make that calculation, you're going to have to use 15 volts for your voltage drop across that capacitor. And you're going to multiply that by its capacitance and get 0.012 coulombs. Okay? The next thing that is asked of you is what's going to happen now if you open this switch back up and you close switch S2. And they ask you about steady state. That's another fancy term for after a long time. So after a long time, there's not going to be any more charges flowing from C1 to C2. But that doesn't mean they'll both have 15 volts across them. In fact, I know they won't, because as charge leaves C1 and goes over to C2, it's going to lose voltage and C2 is going to gain voltage. That process is going to keep on happening until they're both at the same voltage. And so to answer question C, at steady state, we need to look at this fact that at steady state, the voltages across them will be the same. And so the charge divided by the capacitance will be the same. But remember, free response, AP always loves this.